Hi everyone and welcome to this online presentation at PLEA 2020 of a technical paper titled Overheating Risk in Social Collective Housing in the Basque Country and Navarre built under the Passive House Standard. It is authored by Professor Dr. Rodriguez Vidal, Professor Dr. Orey, and myself, Jorge Otay, who will be explaining the monitoring campaign and comfort analysis we performed in a 171 building in Bilbao, Spain. The origin of this study is the European directive that establishes that we should all be doing net zero energy buildings. The problem is that if you take too much effort in energy efficiency, but you don't do it right, you can generate a new problem of interior comfort that in our temperate and hot climate is overheating. It's a well-known project. This study was developed in two phases. The first one consisted on dynamic simulations in the most common typologies, social housing in the Basque Country, and in the second phase, we chose a case study, evaluate a tower, and set up a monitoring campaign and performed a complete post-occupancy evaluation with surveys in this case. This is a copy of the Passive House certificate of the case study. It's a 27-story tower, the highest Passive House certificate building in the world right now. We have highlighted the overheating numbers. The design team calculated or simulated a maximum of 7% of hours of exceedance over 25 degrees, which is compliant with the maximum set by the Passive House Institute of 10%, although it is above the recommended 5%. When you surpass the 15% mark, this is deemed as catastrophic by the Passive House Institute. You should keep this in mind because we'll discuss the results of a monitoring campaign later. We've also used apart from the criteria of the Passive House Standard, some other criteria like those contained in European Standard 7730 and in European Standard 15251, which is an adaptive model. We have also used three other standards, British standards, ones developed by ETSAC, the British chapter of Building Service Engineers, TM52, CIPCA and CIPSE TM59. This is a chart explaining which standard you should use in each case. You can pause and see it with more entertainment. You should carry on. This is a photo of the building in the left, and on the right you can see the spatial distribution of the user comfort survey takers. They are fairly well distributed throughout the building, which was something we were looking after. We did it using Google Forms, and here we have brought for show one of the most important questions, which says, do you have any difficulty sleeping during the summer due to lack of comfort in your house? Where 94% of user takers responded that yes, they do have problems sleeping due to excessive heat. Then we proceeded to establishing a monitoring campaign in 4 dwellings with different occupations, different orientations, different floor area, different level, and different bedroom number. We have since then added 2 more housings and are also monitoring the common spaces of the building. You can see a full description of the equipment you used in the technical paper. We used an FTP network to send the data to us, and then to obtain the exterior or the outdoor climate data to perform the adaptive comfort model analysis. We took the data from a nearby meteorological station 500 meters away from our case study called Abusur. These are some depictions of the simulations performed in the first phase of the study and the conclusions of it. Most notably, it is the need of sun protection from mid-April to the end of October, and also the high rates of natural or mechanical ventilations need to maintain comfort. The results of the user comfort survey show that all of the users, 95%, deemed the temperature at their homes to be too hot to be comfortable. This was confirmed by the clothing they reported to use, which on average was of 0.27 claw value, equivalent to wearing only underwear. These are some comments by users. You can maybe pause and read them with more entertainment. And we arrive at the first recorded data for doing number 1, which is a 3-bedroom apartment located on floor number 27. The maximum recorded temperature was 29 degrees. And of the 3,672 hours of the summer period, 1,790 were over 25 degrees Celsius. That is 48.7% of hours of exceedance. The hottest and most humid month was July, with 84% of hours exceedance, and then August and September had similar values, over 70% of hours of exceedance. In the winter, with the same 730 standard, we can see that the problem in the summer carries over to October, which is in the European standard considered to be a winter mode, but we see that no longer in Bolueta is a winter mode, because we have temperatures over 25 and over 27 degrees for most of the month. These are the same analysis performed, but under the adaptative model of European standard 15251, and same with another adaptative model in ETSAC-UDC. We then proceeded to analyze the problem of the nighttime comfort using also ETSAC standards. Nighttime hours in summer in June 1 were 24 degrees were over 61%, while nighttime hours over 26 degrees were 16%. The maximum temperature recorded at night was 28 degrees. This is a table that summarizes the number of hours over 25 degrees broken down by month. It is remarkable how some of the dwellings can exceed the 7% stated on the certificate, or even the yearly limit of 10% set by Passive House, with data of September and October only. We then did some projections because we had incomplete data in some of the dwellings from the data contained in dwelling number 1, and same with nighttime temperature studied with ETSAC-TM59. I should remember the limit set by ETSAC-TM51 for naturally ventilated dwellings is only 1% of hours for over 26 degrees. We have here 9%, 30%, and so on. This is a table that summarizes the whole compliance with the different standards we used. We can see which of them comply and which ones don't. So the discussion of the results and the conclusions we obtained